So our first speaker is Pierre Moreau.
Moreau, yeah.
from Plastic Energy, who are actually based here on our campus in Loughborough, so it will be great to hear from him.
Thank you. Sorry. Yep. So thanks for coming. So we'll talk about acceleration of end-of-life plastic chemical recycling by catalysis. So yeah, first talk about us, Plastic Energies and the catalyst solution we developed. How did we improve on that performance? Then how do we model the reactor to the full scale? And then conclusion, future work. So Plastic Energy, who we are. So Plastic Energy is a global recycling technology company, headquartered in London, and we have 2 operational plants in Spain. So our team has developed a unique patented TAC process, and this process converts end-of-life plastic into an oil called TAC oil, and that feedstock can be used to recreate some virgin plastic. And we are the only global company that have successfully and consistently produced enough TAC oil or oil to enable conversion back into plastic. So I think everybody by now should be aware of the plastic crisis, but just a few figures to remind. So the plastic use has been increasing 20-fold over the past 50 years. Every day, more than 1 million tons of plastic are produced worldwide. Each year, more than 8 million of plastic leak into the ocean, and only around 14% of plastic packaging is recycled worldwide. So why chemical recycling and nothing else? Well, you can increase the recycling rate, you increase the quality of what is recycled, and you support sustainability goals. So here is a little schematic of what is happening recently. So you got plastic created at the plant, then as a consumer with them, and basically you go to waste, and you go the linear way, going to landfill and then leaking into the ocean, or you go to incineration and then you pollute the environment too. Or you can go to a mechanical recycler and then go back to the plant. However, not all plastic waste can go to mechanical recycling, unfortunately. So some are diverted to our plant, TAC plant, produce an oil. That oil can be used to make more plastic. We go back to the plant, we can use again, and so on. So we create what we call a chemical recycling loop. So who we are? So we're industry leader in chemical recycling. Been developing our TAC process over the past 10 years. We got 2 industrial plants in Spain that have been operating continuously for the past 6 years. We have validated and certified the plastic-to-plastic process, and we got long-term partnership with major industrial players like Silder, for example. So what is our mission? So first is to reduce pollution, so it is to divert end-of-life plastic, for example, from leaking into the ocean. It's to create a circular economy. Is to increase the recycling rate, increase the quality of what is recycled so that it can be used for food grade, can reduce the oil dependency, and it can also boost local economies and create new jobs. So what is our feedstock? So it's mainly mixed multi-layer post-consumer plastic waste. There's no need to wash or separate by color or polymer type. Preferred is LDP, HDP, PP, PS, end of life. We can still process, but in lower quantities, PET, PVC, EPS, and category 7. So we produce an oil that is called TAC oil, that is shown here, and this is what we use as a feedstock. You can see it's really end-of-life plastic. That oil can be used by the petrochemical to the steam cracker to produce more olefin. So the olefin then is going to be used for polymerization to create new plastic. So here is a little schematic, very simplified schematic of our process. So the plastic is coming on conveyor belt, is melted, then it's going into a reactor at high temperature. The plastic is converted into a vapor. That vapor goes into a condenser where it is separated between gas and TAC oil, and TAC oil is then stored before being sent to a petrochem. So what is the catalyst solution we develop, and how does it accelerate the chemical recycling? First, I will take a step back. What is a catalyst? So it is, and what is catalysis? So it is a process of increasing the rate of reaction by adding a substance, a catalyst. Certainly, the catalyst is not consumed, and remain unchanged after it. So what does happen? So it opens a different pathway with a lower activation energy. This results in a higher rate of reaction. So basically, you do the same thing, but just higher speed. The final results on the thermodynamic are the same, and catalysts are widely used in the industry, and it's estimated that more than 80% of any chemical product has undergone at some stage a catalytic process. So we've been focusing on zeolite. So what are they? So we've been focusing on the ZSM5 zeolite, developed by what is nowadays ExxonMobil, and it is an aluminosilicate belonging to the pentasyl family of zeolite. It is characterized by silica to aluminum ratio, internal pore channel, here, two direction, and external surface area, porosity and presence of micropore, mesopore, and acid number and strength. It is widely used industrially for catalyzing different reactions with hydrocarbon, including carbon-carbon bond cracking, isomerization, dealkylation. Almost any refinery in the world uses zeolite. And it is produced at ton-scale in the industry. So this material has consequently a lot of potential for catalyzing the end-of-life plastic pyrolysis and therefore accelerating chemical recycling. So how did we start? We start very simply by having 5 zeolites from Zeolite International, a major zeolite producer, with different silica to aluminum ratio between 23 to 280. We have here at Loughborough 2 micropilot with 300 milliliter reactor. So before reaction, the SM5 has been calcined to 550. It has been paste, crush, and sieve between 125 and 250 micron and mix at 0.5 weight with the plastic mix. So this is the plastic mix we use that is basically representative of what is in your waste. And the reactor is purged with nitrogen overnight, so it's happened in aerobic condition and tested at lab standard operating condition. And to our great surprise, we realized that the most acidic zeolite, which when you think about it should be the most active, are actually the least active. When you go to high silica to aluminum ratio, you got less size, so it is normal to see that it's actually less active. So consequently, the two base zeolites are the 80 and 50 to 1 silica to aluminum ratio. I say this comes as a surprise, and the idea of silica to aluminum ratio to maximize both activity and selectivity to tackle is a 50 to 1. So since we managed to explain the results, so we observed that basically when you go to the most acidic one, you got an increased rate of coking. So coking is poisoning by carbon. And that explains why the zeolites show less activity. So how did we improve on that performance to try to improve the rate of fraction, try to improve the recycling? So I always go back to that slide that I call the 4 circles of catalysis science. So you got synthesis, you need to make your material, then you need to characterize it using a lot of technique, then you need to test to your micropilot for performance, and then you model that performance in the full-scale reactor. And what you get in the center is the knowledge. So how did we get on with matching characterization and performance data? So we use a software. It is widely used in the industry. It's called GMP software. It's a statistical software that will look for any correlation possible. So I've been using that to match the physico-chemical characterization of the zeolite with the activity of that zeolite. And we found 2 parameters that are actually the same, but they're just explained differently. So the mesoporous volume and external surface area of the zeolite linked with the activity, showing that the biggest is the external surface area, the highest is the activity. So we found a way actually to improve the activity of the zeolite. And we show also that suggests that the pyrolysis happen on the external surface area of the zeolite. So contrary to a lot of other reactions with zeolite that happen in the micropore. So I've been looking in the literature for different methods on how to improve that external surface area and that mesoporous volume, and I found one that is quite cheap and scalable. It is called desilication. So did we improve that performance? So we've been doing 3 treatments here at Loughborough in reflux at 80 degrees C for 30 minutes with sodium hydroxide, so really an inexpensive chemical. 3 different concentrations. Then we did free exchange in ammonium nitrate at room temperature. Then again calcination at high temperature. And then the CSM5 is still pelletized, crushed and sieved between 125 and 250 micron. Then we did some characterization by nitrogen physics option. And what we observed is that for all the zeolites that have been desilicated, the mesoporous volume and the external surface area is increasing significantly, even for that zeolite is more than double. At the same time, we saw that the microporous volume is decreasing. This is normal since you got raw blocking by silicate, which is a byproduct of the reaction. So then we try to find a quick test to actually determine the activity of the zeolite. So we've been using a TGA instrument with 3 ramp rate at 5, 10, and 20 degrees C. And then we've been trying to determine that equation here by determining pre-exponential factor, activation energy, order of reaction. So we use the Kissinger method to determine the activation energy and pre-exponential factor code, and the Refern method for the order of reaction. And then we did the final optimization using the Excel server. And what do we see? So we see that basically all the reactions are first order single reaction. Activation energy doesn't change much, but the pre-exponential factor is increasing a lot when you do desilication. Like that zeolite, it is an increased fold of 100, which is huge. And this shows that we have improved absorption and desorption of the reactant and the product. So then we've been calculating the rate of reaction for all those zeolites and the zeolite non-desilicated and the no catalytic case, so basically the purely thermal. We then, for ease of comparison, normalize the no catalyst case, and you can see that whatever zeolite tested, there is a significant increase in the rate of reaction. Now if we normalize to the benchmark that is non-desilicated, we can see that that zeolite is showing a significant increase in activity compared to the benchmark. So that is that formulation that then we've been deciding to scale up at our third party. So yes, we managed to find a method that allows us to increase the rate of reaction quite cheaply. It is scalable. It is actually currently scaled up our third party. And also that demonstrates that basically the LDP pyrolysis happened by pore move and kilocatalysis. So this was developed by Johan Mertens in the year 2000, this concept. I was actually working on this also during my PhD. So that means that the reaction only happened on the external surface area or at the pore move of the zeolite. So then, using all those kinetic equations, we've been using another software called Aspen Plus Dynamics, and we've been building a model of our reactor. As input data, so we input the kinetic equation, polymer properties, polymer melt properties, product distribution and properties, reactor geometry and dimension, and output data with batch time, reactor polymer melt and field level, etc., etc. You can have really a lot of output. So what are the results? So we did 3 cases. So we did 1% ZSM5 in weight, 10% weight ZSM5, and no ZSM5. All the results have been normalized to the no ZSM5 case for ease of comparison, and only shows a pickup free output. So there is the batch time, there is the maximum level in the reactor of the melt, there is the maximum reactor vapor flow rate. So if we see that with 1% of the ZSM5 we got a decrease, obviously in batch time, but it is not that much. Now if you put 10% of the ZSM5, you got an increase in of 2.4 in throughput. As expected, the level in the reactor is lower, and the maximum reactor vapor flow rate through the contactor is higher. But this is not an issue in our case, since basically that flow rate through the reactor is still below the maximum allowable flow rate. So now, also what we observe in the 10% case is that the batch time was actually just finished when you stop feeding the reactor. We just showed that, so I was wondering if basically the feeding stage was the limiting stage. So what I did in the simulation is that I decided to double the feed rate. And then you can see that the increase is higher, actually, 3.3. So that shows that with the thermal pyrolysis, basically the reaction rate is a limiting factor. With catalytic pyrolysis, then that's the hardware and that the feeding rate that becomes a limiting factor. So basically it's not that the catalyst is not good enough, simply that you need to improve your hardware or optimize your plant. So as a conclusion, so we found the ideal silica-aluminum ratio to maximize plastic pyrolysis. We found a cheap way and scalable way to actually increase the rate of reaction, so to increase recycling. Managed to show that the reaction happened primarily by pore move and kilo catalysis. So the reactor model has confirmed what we saw at the nanoscale. That means basically at the 10% loading, we can increase the feed rate by 2.4 standard feed rate, 3.3 for double feed rate. And that basically the reaction is limited by the reaction rate for thermal pyrolysis, feeding rate for catalytic pyrolysis. And my final word on that is that the plant needs to be optimized to harness the full potential of the SM5. Currently, it is optimized for the thermal case. It is really two different optimum. So future work. So now we're quite excited. As I am currently talking, the third party should be desilicating the scale-up batch in their own facilities somewhere in the world. And we go to kilogram scale. Then should arrive in June, July this year. And then we'll test in our pilot plant here in Loughborough. So pending success, then there will be a scale up to ton scale, and then the demonstration run at the plant in Spain. So finally, a thank you to the whole team here, without whom all these results and all that presentation would have been possible. So thank you, Emily, Daria, Abby, George, Alex, Andrew, David, and Anthony. And thank you for your attention, and I'm open to any question.
Thank you very much for your presentation. I think we've got time for a couple of questions from the audience. Yes, Jeremy.
Can you say something about the stability of the pyrolysis soil? How long it remains stable and how easy therefore it is to transport? That's the first question. Second question, how does your technology compare with other pyrolysis soil technologies? And thirdly, if I may, what is your business model? Are you selling the technology, or are you selling the pyrolysis soil, or something else?
Okay, so let's go one by one. So mainly the first one is about the stability. So you need to look at stability. So of course, it's happening in aerobic. Cannot talk a lot about that. We put a lot of effort into that. So a lot of things are proprietary.
Yeah.
But yeah, you need to look at that. Going to your second question, there's pyrolysis oil and pyrolysis oil. And our process, I would say, when you hear and ask people, yeah, it's rather on the top grade of pyrolysis oil compared to other manufacturers. And of course, different pyrolysis have different stability, but it is not different, for example, compared to people who do FCC have the same issue. So there is on the market different manufacturers that supply some compound can be added, and there's different techniques you can improve. So basically but let's take even the big picture. So we've got currently 2 plants being built that are just by a petrochemical complex. So one is in Geleen, with Sabic, in south-east Netherlands. And it is right by the petrochemical complex. Going to go through an do Twitter. So in that case, the stability is not an issue. It's going to go, I mean, the plant is there, the hydro heater is there, the steam cracker is there. So that's going to work. There's another one in Le Havre, I'm not sure what they will do, but it's basically by the steam cracker. So 2 plants in Spain are located in Seville and Almeria. And basically, there is a tanker coming, taking the oil. So we do things to stabilize the oil, and we do some treatment post-reactor, but I cannot tell any more about that. It's confidential. So I think that's the answer to your first question, I think.
Sorry, yes.
Yeah, and the second question was about the quality. So I would say, yeah, the quality, there is a lot of different way you can do pyrolysis. So it's a bit like catalyst. People use catalyst word a bit for everything, and then they lose it. So pyrolysis is the same thing. So I think our pyrolysis oil, compared to what we saw from some competitor, is rather on the top on stability, color, etc. We're still working on that. We still got development on that, and we still have a full analytical lab here in Loughborough where we measure different properties like density, color, etc. And each batch also, of course, at the plant is also going through QC. So sorry, what was your third question?
Your business model, are you licensing or are you going to be manufacturing?
So we started by owning the plant. So I think the first plant you need to own them, really. Since if you hand over to somebody else, then it's never going to do exactly what you want. But now we have started, and that's on the website actually. So I will encourage you to go to the website. We go with a French company that is called Accents, which is linked with ISP. So I did my PhD with ISP, so I know very well Accents. So actually they are going to do licensing for us. And we've got a project, we got already some licensing in Australia, we got the Kenos project, so that's also on the website. I think that was announced last year.
Thank you, Pierre.
Yeah, then basically, yeah, just to finish on the licensing, then basically, yeah, I mean, you see how much plastic is produced every day. I mean, it's going to take some time. So to leverage, one way to leverage basically the engineering of other people is to do licensing, and then you don't have so much work on your own engineering team. And that's a good way to actually increase the number of plants you have working for you.
So given the theme of you're not part of the panel discussion afterwards, but I want to ask you, I mean, you've developed the technology in the UK, but all the plants are being built abroad at the moment. So what's stopping Plastic Energy from building plants here?
So it's worth doing a bit of history. So Plastic Energy before was called Cyanide. So first, the technology is very good. It's organized robot. So actually, that was developed here, like literally, not at the actual part, the chemistry department, and also where it was before there was a move. So it's really a low-bar technology. The laboratory is still here. So there is, you saw the team here. So this is the lab we have here, since there used to be an old British gas lab. So part of the lab has been converted just recently so we've got 2 micropilot, we've got a larger pilot, a 30-liter reactor pilot coming in June this year, and we got a full analytical with different GCMS, boiling point curve, etc., density, color. Got our headquarters in London, where we have engineering. We've got also a lot of people. People have been talking about policy this morning. We know very well about that. So we've got people who are working full time on following the different policies, what is done in the UK, also in the EU. We've got also lawyers, etc. So we're employing people in the UK. However, it is true. So what happened at Cyanide? So then Cyanide was bought by one of our customers that was called Plastic Energy, which was a Spanish company. So this is why the 2 plants are located in Spain, Seville and Almeria. What I can say is that so we got also two other projects. So we're building 2 plants on continental Europe, just not here. So I mean, we have projects worldwide. We are not forcibly looking to build in the UK. I mean, as I say, that's going to come one day. We have several inquiries in the UK from British company about our company. I mean, we've got inquiries basically from any continent in the world. I would say that it's very hot currently in Asia. I mean, we got recent announcement with SKChem, so the Korean, etc. So we don't foresee look to build a plant somewhere. So we're open to anywhere in the world. I mean, we've got also people who are working for us in USA, etc. So it's really global.
Okay.
That's going to come one day, John. Don't worry, there will be a plastic energy plant in the UK.
Okay, so thank you very much for your presentation again.
You're welcome.
And yes, the next presentation is from Professor Aidong from Oxford University. So your slides should be here, hopefully.
Okay, good afternoon, everybody. So my talk is going to be a little bit away from chemicals, plastics, but looking at some of the work we have been doing on the resource circularity for food production, which is in the context of bioeconomy. So I think probably the term bioeconomy was mentioned at least once this morning in one of the talks. So it's a very wide concept. I think generally people say it is about all the activities involving the production and use of biomass, or the use of bioprocessing or biotechnology to produce products and services. So if you look at the economic sectors, again, we have all the primary production sectors: agriculture, fishery, forestry, but also food manufacturing, and also a big proportion of food, material, and energy sectors. And of course, waste management is always a key issue within bioeconomy. So some of you might already know, in this country, in the UK, the bioeconomy is a big economic section. So we have got some numbers slightly dated, because I think this is the latest, this is from the latest report from the UK government, which was already 10 years ago, roughly. So it's a big economic size with a lot of employment. And within that same report, there was a very ambitious projection of nearly doubling the size, economic size by 2030, which is not too far away from us. So economically, bioeconomy is very important for the UK. I suspect it's also quite important for some other countries. But the problem is, at the moment, bioeconomy is far from resource efficient, environmentally sustainable, and is also not one of the things that bring most contribution to the social economic resilience. So we look at some of the figures in the UK. So first of all, the bioeconomy is a big contributor to the solid waste. More than 50% of landfill come from bioeconomy. And also looking at the greenhouse gas emission, it doesn't look very nice either. So it's around 14% of the total greenhouse gas emissions from bioeconomy. And this is excluding the emission from energy use. Okay, this is so-called direct emission. So it's a lot of contribution from bioeconomy. And some of you might already know this fact. So the bioeconomy, unfortunately, discharges a lot of nitrogen and phosphorus into the aquatic environment, causing a lot of problems from the environmental perspective. And also, that represents a huge loss of resource if you compare the total amount of NRP being discharged from the bioeconomy and what we get from artificial or chemical fertilizers. So this is from resource, from environmental perspective. But in terms of economic resilience, although we have a big size, in the UK in terms of the whole bioeconomy, and food production is a big chunk of it, but unfortunately, in terms of the food supply self-sufficiency, it is really not offering a lot. Only about 50% of the UK's food demand is met by the UK's bioeconomy. I don't know whether some of you have experienced this, but at least my household has. Just a couple of weeks ago, we had difficulty getting hold of tomatoes. So we shopped around, but at the end we didn't get anything. So it's probably not one of the most important things, but it represents some kind of problems arising from the lack of self-sufficiency in food supply. And also looking at fertilizer, again in connection with food production. So at the moment, the UK's farming industry, the farming sector, horribly depend on imported fertilizer, chemical fertilizer, and this is quite vulnerable to the international market change. So because of the energy market change and also the geopolitical conflicts, which would affect the international supply of fertilizers. So in 2021, so this is a green curve showing the average kind of fertilizer cost. You can see over the 1 year, it nearly tripled from beginning to the end. And going into year 2022, last year, so the high fertilizer price nearly sustained at least for half of the year. I think the price has just dropped in the last few months. I haven't had the latest figures, but I think these horrible developments cause a lot of problems, great pressure to the farming sector. I think DEFRA has to have some emergency response to help the farmers to deal with the pressure. So this is just to explain in the current bioeconomy, very much because it's kind of linear structure, we have not only economic problems, but also environmental, social problems. So to deal with these challenges, we're in a kind of circular economy kind of event. We would ask, whether if we have a circular bioeconomy, whether this can really help not only with the environmental, reducing the undesirable environmental output, but also to reduce the dependency on external resource input in terms of the national bioeconomy. I think that a lot of proposals, doing circular improvement, so that hopefully we can address both of the problems. So what I want to just briefly explain or introduce is some of the work we have done in the last couple of years, not for the whole kind of circular bioeconomy, but only for this corner. It's about how to get values out of waste and back to the primary production, particularly food production. I just want to acknowledge particularly the contribution of Pierre is one of my group members. I think Pierre is behind all the work that I'm going to explain in the next few minutes. So the first piece of work I want to go through briefly has something to do with producing food in cities. Okay, that is not something that we do at the moment, because if you look at how cities are getting food at the moment, it's mainly relying on external supply. Normally we have food transported to cities from far away, and the distance between food production and food consumption in cities can cause other problems, environmental, resource, or even some social cultural problems. So the thing we wanted to look at is whether we can really introduce food production in cities through something called urban agriculture, and we do that in connection with the organic waste management. So it's really just to build a link between them, because we need to get rid of the organic waste, but hopefully we can use the valuable components like nutrients or energy from the waste and to supply local food production within cities. So we had a couple of questions. We want to understand to what extent we really have space in cities that we can grow food, maybe through some kind of engineered system. And we also need to look at the material flows. We want to see the kind of combination between organic waste management and food production. We really needed to know how much, for example, of the nutrients can be extracted and then can be used for food production. It's very much kind of material flow analysis. And finally, we want to say, okay, if we do that, how this system would compare with the current system, where we get food from far away, and then we deal with waste management as a separate issue. Okay? So, so just very briefly going through some of the options we were looking at. in terms of the source of the organic waste, and different options to treat waste through things like composting, insect rearing, AD, and also a number of kind of possible growing options that we can use in cities, and hopefully we can get vegetable, fruits, and fish through some of the systems to supply the urban population. So probably I'm going to skip the modeling approaches. We need to do a lot of kind of GIS mapping, understanding the space availability, understanding how things can flow, how we can optimize the distribution of waste flows through different processing options and into the food production. Just say that we applied this to 2 case study cities, to European cities. One is Glasgow in the UK, and the other one is Lyon in France. So these cities, you can imagine Glasgow is a much larger area, and the population density is lower than Lyon, but Lyon is warmer, so it's better for food production. But Lyon, being in France, has got a lot of advantage in terms of the low carbon footprint of energy supply. Because when it comes to producing food in this kind of artificial environment, energy supply is a big issue. And Lyon does have advantage in that sense. I think I'm going to skip this. There were a lot of discussion about LCA earlier, so we also needed to do a reasonable job on LCA, because we really want to compare, among many other things, just the carbon footprint between this integrated system and current system. So we had, looking at the population, the consumption of food. The food can come from external supply or from a new UA system, the urban agriculture system, and the waste conversion can either be done in a conventional way through some external treatment like landfill or incineration, or we can supply this to the urban agriculture. So the life cycle greenhouse gas emission have been considered through through all the terms, and hopefully this would allow us to compare different options. Just to show you, I think what is shown on the screen is to what extent we can supply fruit, vegetable, and fish to these 2 cities. As you can see, this is across 12 months, so a year. So in Glasgow, it looks like the self-sufficiency can be achieved, particularly in the summer months, in a very high level. In Lyon, the self-sufficiency achievable is low. I think that's mainly because of the area available in the cities, because Lyon has got the higher population density. So what about greenhouse gas emissions, the carbon footprint? So we were looking at, again, each month, how this integrated system would compare with conventional food supply, which is basically getting food from far away into cities. So unfortunately, you can see, particularly in the colder months, in the winter, in the early spring or in the winter, this long bar, this is from the urban agriculture with food waste measurement. So you can see the greenhouse gas emission is much higher than conventional one, which is the lower bar. In the summer month, this new system would outperform conventional systems. I think this comparison is mainly because of energy consumption. So in the winter, when the temperature is low, in order to run the greenhouse, for example, you do need to provide a lot of energy. The situation in Lyon is very similar, although the difference is smaller, again, thanks to the low carbon footprint of the energy system in Lyon. So I think I'm going to so this is some details about the material flow. We optimize how we can get the different waste flows through different waste processing options and getting into the food growing systems. So I think I'm going to come back to this slide in a moment, but just a little bit on the comparison. So we showed you, I showed you, how things compare in different months, but across the year, in average, we can see this is Glasgow and this is Lyon. We have 3 systems. So this is the current system. which is, as I explained earlier, we buy food from external world, and then we have a standalone waste management system, and this is the urban agriculture system plus a standalone kind of waste management system, and the third one is the integrated UA plus waste management. We can see that this current system, in terms of the carbon footprint, is still better than any of these two new ones. Again, it is about energy consumption, although this integrated system does outperform a system where we have separate UA and waste management system. But this is mainly from food supply perspective. But what about from waste management perspective? So we ask question, so if in both cities, if we have got a UA system, urban agriculture system, then would it be beneficial to link the organic waste management with this existing UA system? And how does this compare with a system without UA? And from the greenhouse gas emission perspective, the comparison seems to be rather apparent. So this is a system without the UA, so we have quite some greenhouse gas emissions. With UA, we can achieve some of even negative emissions because of the replacement of the chemical fertilizer in the UA system. So this is a net effect. So that is from the waste management perspective. If we can integrate food waste or green waste management together with UA, the carbon emission will be much more reduced compared to a standalone system. So this is the study we did on the city level. Before I leave here, just want to come back to this diagram again. So one of the things that we would like to point out is that although we try to make our best to use the urban agriculture to absorb waste, but actually the total amount that can be absorbed is rather limited, because you can see a lot of waste processing activities wouldn't produce output that can go into the UA. That is simply because we just produce too much waste in cities. Even you have a full-scale UA, you wouldn't have enough space to absorb all the waste. So that means to really address the organic waste management problem, you cannot just look at the city. You have to look around at the region level. So I think we wouldn't have time to look at this second piece of work in detail, but maybe I can just show you some of the key learnings. So what we did was to look at not a city, but a region. So in this case, this is a Porto region in Portugal. So it has got 7 areas and 76 districts. So it's a combination of towns, small cities, and farming communities. So, and there we were looking at, in the whole region level, what are the kind of the options for organic waste management, and how do they compare? So I'm going to skip a lot of details, but I want to take you to one of the key results. So we were looking at economics and also greenhouse gas emissions. So in this case, we did care about the cost, because this work was done with the local waste management company. They really wanted to understand, which option would save money, which one would cost more. So among all the options, like composting, AD, localized system, centralized system, incineration, and we were able to see some kind of overall champions. But actually, what is really important is that earlier I mentioned there are 76 districts, right? So between different districts, you can see, I think this is one of the options. It's called local composting plus urban agriculture, and this is the anaerobic digestion. So look at this system, right? It becomes rather cheap in some of the locations, but it becomes very expensive in some other districts. The same thing is true for AD. So there's a lot of difference between different districts, even within the same region. Okay, and we asked what is the cause. Actually, this has a lot to do with what we call discrete typology. It's mainly population density within that region. So in a densely populated regions like here, the centralized options such as AD looks much better, but in the rather remote areas, these more localized options is much better. this has a lot to do with logistics, basically waste collection, transport, so that makes a huge difference. Similarly, we see the same patterns in terms of greenhouse gas emissions. I think I'm going to just skip these details. So before I stop talking about this topic, I just want to share a couple of other things we have observed in our recent work. In terms of, when you try to close a loop within the context of waste management, food production, or even bioeconomy, one thing I want to mention is something to do with energy. I think this is a topic that was mentioned many times this morning, even for chemical production or plastic conversion. So within the context of our work, we wanted to look at, so if we try to have a more kind of closed loop food production, you try to produce food at your doorstep so that you can have a smaller circle within the system and to increase environmental sustainability and food security. One of the things you have to do in the urban region is that you have to grow this in controlled environment because you haven't got a lot of open space. And as I said earlier, energy consumption is always the issue. And if you want to achieve low greenhouse gas emission, you have to use renewable energies like wind and solar. And then there's a problem. To get wind and solar, you need land area. Okay? I think this was also one of the points made by one of the talks this morning. Then the question is, within cities, can we find this enough space so that we can achieve both food independency and energy independency? We were really not sure about this, so we did a study looking at a typical kind of vegetable basket, looking at 9 world urban regions and did the assessment. And it turns out that we don't have to read this whole thing in very detail, but I think here this shows the total area available for renewable energy production versus the area required to produce energy only to power UA, only to power greenhouses. Okay, so you need something of value larger than 1, so that you have enough land only to get energy. And all the areas shown here are feasible, but unfortunately there are areas where we have a problem. You don't have enough land to produce wind and solar energy in order to power your local greenhouses. I think Japan is one of the areas, and Singapore is another one. And maybe just very briefly, there is always the issue of when we introduce circularity, there is always a challenge to look at disruptions to existing logistic networks. So this is just very quickly is an example from our recent analysis of the Leicestershire, which is very close to this point, I think, right? Look at organic waste, particularly food waste management, and we wanted to look at how we can introduce a circular system for this region. We started by understanding how people are doing with food waste in that region, where they are sending food waste, and it was to our great surprise. You can see. So this is Leicestershire. They send food as far as to, in York area, Southampton area. And so when we look at it, we thought, oh, come on, why people do that? Well, this is what people have been doing for maybe 10, 20 years. So we're still in the process of understanding why this is happening. But the message here is that we can do a lot of calculation on paper, get a nice arrangement about materials, but at the end of the day, things have to happen on the ground. We need to introduce probably a new logistic network which can be rather different from here, and it will take a lot of time to go from where we are to where we want things to be. I think I'm going to just wrap up very quickly. This is a slightly different topic, looking at nutrient recovery and food production. But I think within the area of bioeconomy, understanding the regional characteristics, understanding that the impact of that on the solution is very, very important. I hope some of the examples you have seen to explain this point. And also a lot of complexity we need to consider when we want to implement a change. I think I'm going to stop here. Thank you.
thank you very much for the very interesting presentation. I'm sure there will be a lot of questions. I think we've got time for a few. Yes, Amy?
A couple of things. We've had quite a lot of venture capital investment in urban farming, which just in the last few months, a lot of those businesses have failed. So again, it's this nice in theory when it hits reality, things don't always work out. Have you kind of considered the failure models of those businesses and whether it's applicable to the models you're looking at? But also this morning when we talk of using bio feedstocks for chemicals, yours is kind of sitting to the side, using the biostocks for food. Is there plans within this, within the NICE Centre to look at this more holistically and actually say we've got lots of people who want this waste material, this virgin biomaterial, where should it go, given our chemical and food needs?
I think there's two questions. I think the first one is very interesting, but I think from our modeling work, the economic viability of this controlled environment farming, a lot of this is really about energy. It's really energy. I think I mentioned the salted root tomatoes. I think then I understand why we have the salted root tomatoes. I think it appears that some of the UK growers reduce their production because of the energy price. I think the current growers probably just use not this plant factory fully controlled environment. Even with these rather simple greenhouses, the energy consumption is already very high. But with the vertical farming, with this multi-layer plant factory where the light supply is completely artificial, and you require 100% air conditioning to run the system, the energy consumption is going to be much higher. So I think that should be the main barrier. And the current energy system price, that doesn't help either. I think that is what we have seen. The second question, I think, is very interesting. In fact, we are in discussion with some of the colleagues here, looking at, because in bioeconomy, we have talked about NNP. Certainly carbon is always there, right? So looking at the possible connection between food, chemical, material, energy productions within what we call this carbon, nitrogen, phosphorus nexus, I think that is going to be a very interesting area to look into. And there, I think a lot of different technologies should be combined. In fact, this is also part of the thing we're discussing with colleagues, ranging from bioprocesses to electrochemical processes. I think the key question is how we can, when we develop the individual technologies, how we can always keep in mind, right? So we're not just looking at carbon, just looking after N, not looking after P, but C and P, they are together. So how we can always keep this kind of holistic thinking in mind, I think that is going to be a very interesting challenge, but also opportunities for future research.
Okay, any? Jeremy, yes, go on.
I like the idea of urban farming. Two things worry me though. One is it affordable, because one of the biggest costs in farm operations is the cost of labour, so can we afford labour here? And the second one is it's safe. I've been to some megacities around the world where the air pollution is appalling. I was always advised by my mother not to make batteries built up environment. So do you have a filter the air?
Yeah, I think both of these issues are very, very important. I think for the labour one, Pierre, the student I mentioned earlier, I think when he studied his PhD, he was looking at some of the business cases. And what he told me is that he observed the use of robotics seems to be getting a lot of interest from this industry, precisely because of labor shortage problem. And I don't know how mature the use of robotics in this area is, but it seems to be a kind of one of the commercial trends. The pollution, the safety issue is very, very important. We read a lot of rather negative stories about urban agriculture. I think at the end, we think if you really want to maintain the food standard, growing food in controlled environment, not in the community garden, so to speak, might be the main approach. At least, unless you want to treat it as a hobby, right? You want to grab a piece of cucumber from garden, that's fine. But if you want to make this as a viable supply for the larger population, more engineered system might be the way to go.
Yours a final question from Simon.
Well, yeah, it's about rest issue and what it does with its food waste. I'm glad that I compost at home, to be honest with you. So is that just a lack of political will? Why? I mean, it strikes me as the conversation that happened yesterday about we should do certain things that we can do now. And what is, you kind of sort of touched on it, but what is the real barrier?
So the Leicestershire case study, this is something we're working on now. So we have just been mapping what's happening. We are in the process of discussing with county council people. In fact, we are meeting them in May to see why this is happening, why the better things are not happening. I think, but our guess is that so the current system wasn't formed over one night. It was just driven by economic convenience step by step. There was no kind of top-level design whatsoever. And so if you have got a lot of food waste from maybe a sausage farm, right, and you knew that from your connection, South Almond has got a facility which is very good at treating this at a very low price, in terms of gauge fees, you just go for it. I think things have just developed probably just like this, very pragmatically, primarily driven by economic convenience. And now you really want to turn the tide around. So I think it's going to be hard work. I think from research perspective, we want to point out to people, actually, if you do it that way, it's not going to cost you more. Hopefully that's convincing. But from the political perspective, I think for example, the local authorities, I don't know how much power they have over local businesses. But I think if they can insert, put some influence into the local community with the local business partnerships, this kind of options, just showing people the opportunities and giving some kind of sense of direction, I think that would help.
Yes, I think we will have quite a lot of discussion on that also in our sessions tomorrow. So thank you very much.
Thank you.
Aidong. And the last speaker for the session is Chris Holt from Ensus, and formerly worked for Network as well. So,
yep. Well, thank you for the introduction, for the opportunity to speak today. So, my name is Chris Holt. I work at Ensus as a commercial manager, and I'll be presenting today about how biorefineries can be a hub for a defossilised chemical industry. Who are Ensus? So Ensus are one of Europe's largest bioethanol plants, and they have a production capacity of 400,000 cubic metres of bioethanol per annum, alongside 250,000 tonnes of captured carbon dioxide and 350,000 tonnes of dried solids, grains and solubles, which is a high protein product from a process which I'll talk a bit more about later and was mentioned earlier by Andrea. Ensus currently supplies the transport fuel market with their bioethanol, and across the supply chain the emissions are over 70% lower compared to your fossil fuel equivalent, and that's audited. Obviously E10 has been introduced to the UK in September 2021, so there's that market that does exist within the UK. And just really important, as was mentioned earlier, the UK has a starch excess, but it has a protein deficit, which is really important when understanding how Ensus fits into the UK. And Ensus is also part of Crop Energies, which has 4 sites across Europe with a capacity of over 1.3 million cubic metres of ethanol per annum. So in terms of the sites, obviously there's Ensus based in Teesside and Wilton. There's also a site in France, Belgium and Germany. In terms of the mass balance, Ensus takes feed grade grain, and 1 tonne of grain converts to 300 kilograms of sustainable ethanol, 400 kilograms of high protein animal feed, and 300 kilograms of biogenic carbon dioxide. In terms of the carbon dioxide cycle, when it comes to Ensus, obviously you have carbon dioxide in the atmosphere, and that's captured by the biomass during its growth. It then enters into the Ensus plant, and the starch in that biomass is converted into carbon dioxide and ethanol. The ethanol then acts as sustainable fuel for the transport fuel industry, converts to carbon dioxide, which is then captured by biomass at the start of the cycle. And the captured carbon dioxide, part of the Ensus manufacturing process, displaces fossil carbon dioxide and is used for pharmaceutical industry along with beverage industry and many others. In terms of a plant overview, first step is milling to increase the surface area of the grain, and then there's a liquefaction step to prepare the mixture for fermentation, then catalysed by yeast, so the starch is converted into carbon dioxide and ethanol, then it enters into distillation, and the protein component of this is retained, and that is separated out, and that is the DDGS, which is produced at the end of the cycle. The process is very resource efficient, so the water is captured and re-enters the start of the process. So if you're looking at that process overall, essentially what we're doing is, say, converting the starch to carbon dioxide and ethanol, which the UK has an excess of, but we're retaining that protein and concentrating it up so it can be used as a low carbon product for the agriculture industry to avoid imports of carbon-intensive protein feedstocks. But in terms of the chemical industry, the areas which are of interest are the captured biogenic carbon dioxide and the sustainable bioethanol. And so, why is there interest in bio-based chemicals? Well, as I'm sure you're aware, net zero is not possible without defossilization of the chemical industry. Even if you can abate or remove your process emissions in your chemical manufacturing, you're still taking carbon out of ground in the form of petroleum and converting it into products which have a thermodynamic endpoint of carbon dioxide. So it's absolutely essential that we utilise sustainable sources of carbon. And it's also important to note that products from biomass are available today at scale. And it's also a unique opportunity to think about how we can utilise the availability of sustainable carbon to grow the UK chemical industry, which is typically a very challenging industry to bring new assets online. So I think it's a fantastic opportunity there as well. And of course, bio-based drop-ins have high potential to be integrated with existing petrochemical infrastructure, perhaps in a mass balance basis as well. So there's a lot of symbiosis which could occur with these supply chains. So, what's some of the barriers and opportunities? Well, I think one of the barriers is an awareness of the importance of embedded carbon when it comes to net zero. But I think there's been some really positive advancements in the past few months. For example, the net zero review, where biomass is specifically mentioned. But I also think there's an increasing acceptance for the investment opportunity that bio-based chemicals and the sustainable carbon can provide. But I think it's important not just to think about, we have to bring the current chemical industry to net zero. We also have a huge challenge whereby the chemical industry is expected to grow really quite substantially on the road to 2050. So we don't just have to defossilise what we have today, we also have to defossilise what we have in the future. Utilising existing assets is essential for viability, and it's a really big opportunity when you have the availability of feedstock in existing industrial clusters, because that's critical for the business case. And integration is really key for the chemical industry, which is why you have in industrial chemical clusters. However, one of the challenges is where, when you're competing with the petrochemical supply chains that are well established, have economies of scale and exist, it's really important to make sure that there's value across the entire supply chain. So you may have, company A at the end of a supply chain that's selling directly to the consumer, potentially at a premium. Well, if they can get additional value out of that, it's really important that is passed up to the top of the supply chain. We have the company producing platform chemicals who are competing with the petrochemical supply chain. However, there's been some really exciting developments in the space because Unilever and P&G have been really open about what they're aiming to do within this area, especially in terms of communication. So I think that's really exciting to see. In terms of ethanol, as a platform chemical, well established. We're also ethanol can space, TRL9 technologies for dehydration of ethanol to ethylene, and it can be utilised as a feedstock to defossilize many different industries such as plastic, cosmetics, pharmaceuticals, detergents, and much more. The main intermediate is ethylene, which is a real hub for the UK chemical industry, and there's a really strong supply chain in this area and associated infrastructure such as pipelines. And this is a great way of trying to think, well, how can we substitute the shale gas which is imported into the UK, which is fossil carbon. But it's also, interesting opportunity to see how you can integrate the two, perhaps on a mass balance basis. And as I mentioned earlier, it's a great opportunity to utilise UK manufactured ethanol to defossilise existing supply chains, but also to think about how can you not just defossilise supply chains that we have, how can we utilise that to grow the chemical industry and perhaps explore derivatives production. And there's some interesting case studies of this internationally. For example, Croda, who are utilising bioethanol to produce ethylene and then ethylene oxide in Atlas Point in the US. Of course, Braskem in Brazil, which are producing biopolyethylene. In terms of carbon dioxide, the opportunities are even wider in a way. It's incredibly versatile due to its chemistry, and can produce transport fuels such as methanol, specialty chemicals and commodity chemicals. And it's really interesting because products such as methanol could be utilised to decarbonise heavy freight, but they could also be utilised by the chemical industry as well. So there's a real suite of opportunities. However, availability is a real big challenge. We have a lot of carbon dioxide which is emitted throughout the UK, but we don't have a lot of high purity captured carbon dioxide which can be utilised as a chemical feedstock. And of course, Ensus are the current largest producer of high purity carbon dioxide which is captured within the UK. So how does this work from a place perspective? Well, Ensus is part of the Tees Valley Process Industry Cluster, as it's based on in Teesside. It's a uniquely concentrated cluster, so the bulk of the emitters are based within a 5-kilometre radius of each other. So there's a lot of opportunities in supply chains that can be taken advantage of, both in terms of tapping directly into the supply chains, but also taking advantage of that existing infrastructure and skills and know-how. Of course, there's opportunities to defossilise and decarbonise the chemical supply chains, but there's also opportunities to decarbonise transport as well as heavy freight. The region has an ethylene pipeline, a PET plant and a polyethylene plant, so there's lots of opportunities within that space within a very small local area. And historically as well, Teesside have the UK's only ethylene oxide manufacturer, which is it's a platform chemical that's used for manufacturing your high-value cosmetics and surfactants. And that supply chain disappeared in 2010. So there's an opportunity to think, well, how about, how can we reshore supply chains that previously existed using the presence of sustainable carbon? And also, due to the really large amounts of sustainable investment in the region, you've got huge investment in carbon capture, over 2 gigawatts planned projects in green hydrogen, 3 different projects in terms of green hydrogen, with one project aiming in the future to be potentially 500 megawatts. That's a huge opportunity to think about how these projects can be integrated together to create truly net zero, sustainable, defossilized supply chains. And in terms of crop energies activities within this area, crop energies have recently announced that they plan to produce an ethyl acetate plant in Germany, and crop energies also acquired a stake in a startup which is investigating the production of sustainable ethylene. So I think it's a sort of clear statement of intent within that area. It's very exciting to see. So just to summarise, bio-based chemicals are one of the few opportunities that we have to produce sustainable chemical supply chains, which are essential for net zero to be possible. These feedstocks do exist at scale. However, new value chains will need to be created in order to make this possible and ensure that partnerships can be formed that are cohesive to economic success. And availabilities of this carbon and bio-based chemicals are one of the few opportunities that we have to really grow the chemical industry and bring new assets online. So thank you all for the opportunity, and any questions?